When someone aims to become a doctor, they will obviously seek a medical school. And if they desire a legal career, they will pursue a university offering a law course. To become a software developer, there are at least three formations: software engineering, computer science, and information systems. What's the difference between them? Stay with me until the end of this video and let's unravel this mystery together. After all, why are there so many different formations related to software development? The problem becomes even worse when companies advertise positions to fill their staff. What kind of professional does the company really need? The use of computers and consequently software development is something very new compared to all other areas to human knowledge, but which nevertheless has evolved at an exponential rate. Since the operation of the first fully electronic computer, the ENIAC, in 1946, information technology has evolved in decades, while other areas of human knowledge took centuries or even millennia to evolve. Perhaps that's why there's so much difficult is establish a common sense of how things work in this area. After all, when people in general begin to get used to a certain concept, things take an exponential leap and change all over again. In this way, to understand why the software development area has been divided into several different formations, we need to go back in time to the beginning of the modern computing and follow how the needs and limitations of each era shaped the creation of new professional roles. Let's start our journey back in time to 1943, in the middle of the World War II. The United States Army, through its Ballistic Research Laboratory, decided to find the construction project of a large computer to assist in ballistic calculations and thus improve the efficiency in the manufacture of ammunition and bombs. For the realization of this cutting-edge project, the Moore School of Electrical Engineering at the University of Pennsylvania was chosen. What was the name given to the project? ENIAC, an acronym for Electronic Numerical Integrator and Calculator. This was the first fully electronic computer composed of circuits and valves. At the forefront of the project were John Eckert, an electrical engineer, and John Mauchly, a physicist. John Eckert and John Mauchly and their team of engineers focused on building the computer hardware. To understand how to perform ballistic calculations and consequently input the calculations and data into the computer, a team of 10 people was created, with 6 of the members being women. Who were these pioneers? Caitlin Antonelli, Jean Bartik, Frances Beth Holberton, Marlene Meltzer, Francis Spence, and Ruth Teitelbaum. Everyone on this team had degrees in mathematics. There was still no programming language or storage device as we know it. The result of the calculations was stored on punched cards. The calculations and data were manually entered into the ENIAC memory through buttons and cables. The division of labor in this project, in a way, shaped the functional structure that is used in many companies to this day. In the American Army, we see the roles of client and project sponsor. The United States Army Ballistics Research Laboratory played the role of the key user, or, as it is more commonly used today, the product owner. Their role was to provide the needs of requirements of the product to be built and validate the calculations results. By focus on building the software, the Eckert and the Mauchly team played the role of the computer scientists. The computer scientist researches and develops new hardware and software, pushing the boundaries of the computing beyond what we already know. Currently, for example, this boundary lies in the quantum computing. The creation of quantum computers will demand the need for the new operation systems, programming languages, database, for example, that fully utilize the resource of the news paradigm. The research and development of this type of software are also the responsibility of the computer scientist. The team of mathematicians worked on surveying and recording the needs and requirements provided by the project's key user. With this information in hand, they worked on creating a specification of how the calculations would be performed. The set of these activities later became known as system analysis. Finally, with the calculations and specifications in hand, the mathematics team could enter the calculation instructions and data into the ENIAC memory to obtain the results of ballistic calculations. Although there was no programming language yet, communication with the ENIAC was done through binary language, the native language of computers. Entering the calculation instructions directly into the ENIAC memory were computer programmed activities so that it could perform the calculations with the data that would also be entered subsequently in the same way as the instructions. As we have already said, the final result of the calculations was printed on punched cards, and thus the role of computer programmer was born, one of the activities of software development. The ENIAC operated for 10 years, and during this period made more calculations than all of humanity had done up to that point. In the following decades, advances continued with the development of various other computers, always with more and more improvements until computers became useful tools for the industrial and commercial world. When entering the corporate world, it was necessary to make some adjustments to the responsibilities and roles required for computer use. At this point, we had a new industry in operation, the computer industry. Thus, computer science as well as the research and development carried out by the new area, computer science, became restricted to this industry and universities. It was no longer necessary to finance a team to develop its own computer. It was enough to buy or rent one from the companies that manufactured computers. Within the corporate world, the role of systems analyst was established, with its traditional duties such as understanding the client's business process, understanding user requirements, analyzing and designing a solution to problems, and eventually programming the software to be developed. In addition to these activities, the system analyst also took on the role of supporting computer hardware and the interconnection between them and their peripherals. Hence, the name of the role, systems analyst or analyst of the whole, formed by its interconnected and interdependent parts. With so much work assigned to one person. That's why some system analysts focus on computer programming activities, thus giving rise to the role of the computer programmer. But note that the skills required to perform both roles are the same. There is no degree or superiority between the roles, only specialization. Normally, a system analyst will be able to create work specifications for several programmers. Hence, the advantage of the role specialization. Over time, it was realized that it was not enough for the professional to work in this area to be graduated in engineering, mathematics, or related areas. A specific degree was needed to train professionals and provide the knowledge, skills, and competence required by the work to be done. This graduation is currently known as information systems. Now, we only need to talk about software engineer and its respective professional, the software engineer. Initially, only systems analysts and programmers had contact with computers. The end user received the processing result through reports. But over time, end users began to use computers and perform their processing activities personally. This required computers to become more and more easier to use, and ease of use added complexity to the software solution development. With the decentralization of processing, through personal computers and computer networks, more complexity was added. And the plain truth is, the easier it becomes to interact with computers, the more complex software development will be. This complexity increased the time spent on software development, as well as resulted in increased production costs and caused quality problems due to defects or bugs. System analysis was born with the mission of understanding and solving problems. However, there was a need for more. It was necessary to estimate project delivery dates more accurately, estimate costs, ensure quality, manage work performed by multiple teams. Engineering, composed of its various specializations was the area of the knowledge with the experience and methods to address these issues. However, the development of software engineering was a gradual process, but much faster than other engineering disciplines. The term software engineering was first used in 1968 at a NATO conference to discuss problems encountered in the development of large software. In 1976, a committee was established within the IEEE Computer Society to study and develop software engineer standards. In 1993, the IEEE presented the definition for the software engineering: the application of a systematic, disciplined, and quantifiable approach to development, operation, and maintenance of software. In 2004, the SWBOK Guide to the Software Engineer Body of Knowledge was launched, which provides the following explanation of its objectives. In this guide, the IEEE Computer Society establishes for the first time a baseline with the body of knowledge for the field of software engineer, and the work partially fulfills the society's responsibility to promote the advancement of theory and practice in this area. This guide establishes the foundations for the understanding and evolving software development in a systematic, looking at the whole, disciplined, divided into disciplines or areas of knowledge, and quantifiable, establishing means of planning, measuring, and predicting results way. The SWBOK guide uses elements from the following disciplines: computer engineering, computer science, general administration, mathematics, project management, quality management, systems engineering. The guide divided software engineering into 15 areas of knowledge. The software engineer by training will obtain knowledge of the 15 areas and may specialize in one or more areas. The areas are software requirements, software design, software construction, software testing, software maintenance, software configuration management, software engineering management, software engineering process, software engineer models and methods, software quality, software engineer economics, software engineer professional practice, computer fundamentals, mathematics fundamentals, engineering fundamentals. We can conclude that software engineering is the result of all the accumulated, refined, and improved software development knowledge over the last 50 years. Now that we understand the origins and the reasons for the emergence of each of the areas dealing with software development, it becomes easier to choose. Computer science. As a computer scientist, you will push the boundaries of computing and participate in the creation or evolution of new operation systems, new database management systems, new programming languages, new application servers, for example. And like the pioneers of the computer science, you may even develop software that we don't even know we needed yet. Information systems. As a system analyst, you can develop various information systems for companies, acting as an analyst or programmer. You can also work as a business analyst, business process analyst, support analyst, and also as an information technology manager. In a way, the systems analyst is a generalist capable of working in various sub-areas of information systems. Software engineering. The software engineer is the specialist in software development of any size and complexity, and can even be used to develop information systems or basic software when computer scientists are acting as key users. This professional is trained to extract requirements for software construction, estimate the size of the software to be built, estimate construction effort, estimate delivery times, estimate production costs, plan software development, build software, ensure software quality, delivery or deploy software, improve development processes, and finally, evolve the software through maintenance. Before our final message, which degree would you choose? Leave your comment, subscribe to the channel, activate notifications, like and share. And now, our final message. The best thing a human being can do is to help another human being to know more. Charlie Munger.